And while we have a lot of progress in some of these biomolecular research areas, one area we don't have a lot of progress is in politics, where politicians continue to like to spin the news. But our third story is that scientists have figured out how to spin electrons.
That's right.
And it could maybe power the next generation of tech. This next research paper is out of the National Research Council of Science and Technology in Korea, most famously known right now for K-pop Demon Hunters and Squid Games.
Yeah.
But Korea has a huge technical...
that's where Samsung is.
Right. Like a huge, in terms of amount of people.
They're one of the big fabs in the world.
The world. Like they have a huge population of like highly technical people. And this study is fascinating. So this was a little bit different for me. So the headline here is turning spin loss into energy. New principle can enable ultra low power devices. So one of the things we've talked about in a previous episode is if we look at all the technology revolutions that are currently happening, the one underlying thing that's true and is a part of the great power war that all these nation states are having is we need more power.
Yeah.
If we want to have all this AGI,
that's right,
artificial general intelligence, all these things, we need a lot more power.
Yeah.
The Chinese are solving it right now by building nuclear at levels we've never seen before.
Yes.
But this maybe has sort of some impacts in this power generation problem set. So
yeah, it lets us. I mean, it lets us do more with less.
Okay.
At the end of the day.
Okay.
Right. It lets us compute more with less. If this becomes an economically viable and a commercially viable product.
Okay.
Okay. So I will give you that caveat, but it's a proof of concept of something that people have been after for quite a while. Okay. In order to get into the idea of Spintronics, which is this new paradigm of electronics.
I think Spintronics was just actually performing at Burning Man.
Is there a band that does that?
I'm pretty sure Spintronics is an EDM DJ, literally.
That's
right
hilarious.
Now.
I hope he's good because Spintronics could be the future of electronics. So in order to really understand the story, I think I've got to tell you a little bit about Spintronics, which is different from electronics.
The only context I have is upspin, downspin.
That's good. Yeah. That's already plenty. Okay. That's already plenty because it turns out the electron has both a charge.
Yes.
A -1, let's call it.
Yes.
And it's got a spin, but the spin can be both +1 and -1. It could be spinning this way or it could be spinning the other way. Mm-hmm. So conventional electronics, like the ones in your lights, in this computer, everywhere else, mm-hmm. right? Most of that is exploiting the charge of the electron.
Only.
Right? It's only exploiting the charge of the electron. Current, for example, is the flow of charge, where physical electrons are flowing, mm-hmm. right? And memory, for example, is the storage of charge. Like a 1 means that your capacitor is charged, and a 0 means your capacitor is discharged. That's how you get memory. And that is pretty soon going to run into some problems, okay? Because Moore's law is not forever. Mm-hmm. You know about Moore's law, right?
Yes.
It's like everything doubles every 2 years,
24 months.
Whatever it is. Well, we're pretty soon getting to that limit where Moore's law is running into fundamental physics.
It's slowing down. We can't get because the idea of that you double the amount of transistors on a chip every 18 to 24 months. We're already at like 3 nanometer chips with like TSMC and Apple.
Yeah.
But we can't. It's hard to get much smaller than that.
It's hard to get much smaller. And the problem we're starting to have is power dissipation. Okay? Because like if we have capacitors that are that small, then now we're starting to get into like, we can't store charge for that long mm-hmm. on such a small capacitor. Mm-hmm. Pretty soon we're going to have to keep like, you have to keep charging up the capacitor mm-hmm. to keep it at that. Otherwise it's going to decay mm-hmm. and then you're going to lose memory, mm-hmm. right? So that's one of the things, right? Silicon chips consume an insane amount of power, right? Which is why everybody's like, oh, like one query in ChatGPT costs this many gallons of water. Okay, yes,
crypto has the same problem.
Crypto has the same problem. Yeah, the other big thing is called the von Neumann bottleneck, named after John von Neumann.
Oh, he did the probes and the bottleneck.
Oh, dude, von Neumann did like
everything.
Von Neumann was one of those few individuals where other people like Fermi would be like, what do you, how did you do that?
Was he a magician more than he was a sage?
He was.
Okay.
He was a magician more than he was a sage. But yeah, he had its caveats. And we can get into that in another episode. There was one thing where he like proved that the Copenhagen interpretation of quantum mechanics was the only interpretation of quantum mechanics. And because it was von Neumann who proved that, everyone else would just not question it. Like if somebody were to question it, they'd just be like, yeah, but von Neumann proved that Copenhagen interpretation is the only interpretation of quantum mechanics, and that would just settle the debate. Right? Which is why it took like 30 years for someone like Bell's inequality, and for someone with different versions like the pilot wave theory and all this other kind of like all these other different versions of quantum mechanics, because literally von Neumann had an incorrect proof to prove that anyways the Copenhagen interpretation was correct. Anyways, but he was an incredibly smart guy, and he actually he characterized this thing called the von Neumann bottleneck now, which is this difference between how memory and processing units work. Okay? Because fundamentally, before we had solid state drives, we had and even now that we have solid state drives, we have this separation between RAM and hard disk. Okay? Right? And the hard disk is where you store your permanent memory. The RAM is where you're doing the computation of whatever the thingy that you're doing.
So, for example, if I want to have if I want to take OpenAI's open source model and run it locally on my computer, I need a Mac that has a lot of RAM. Not necessarily a big hard disk.
Not necessarily a big hard disk, but like something that will compute efficiently.
Correct.
Like currently now.
Right?
And so there's a need for a new paradigm where perhaps maybe memory and RAM are the same thing. Right? And with these increasing demands with AI, big data, and all this other kind of stuff, we want to have a new paradigm where it doesn't cost us that much power to upkeep all of this amount of stuff.
Makes sense.
Okay? And so that's where the idea of Spintronics comes in.
Because there's two paths here. It's just increase the amount of power availability is like the brute force way. And then it's like be more efficient with the power we have is this way.
And like even if we were to increase the amount of power availability, like we'd have to increase the size of our computers because we've reached this sort of limit of how dense we can make stuff before the power consumption per square inch goes away.
Johnny Ive would not be very happy with that.
You know what I'm but you know what I'm saying?
I do know what you're saying.
It's like now we've like sort of plateaued in this landscape. Right? And so Spintronics is this idea of utilizing the electron spin in addition to its charge to store information. And to process information. Okay? So the first big win for Spintronics actually happened way back in like the 1990s when we got hard disks. The hard disks that maybe we don't use today because we got solid state hard disks. But remember the hard disks like way back when like your computer would do the sound?
Oh, I remember.
Right? But there was literally a spinning disc. Like it was an electromechanical disc that was spinning, right? And that spinning disc represented the 126 gigabytes of memory, and everyone was like, oh, 126 gigabytes of memory.
Crazy.
But like that was a big deal back in the day, right? And the inventors of this, they actually discovered something called giant magnetoresistance. Giant magnetoresistance. Okay, and it's this idea that what we can do is just like a transistor. The way a transistor works is you've got like a state of the transistor that lets current through, and then there's a state of the transistor that doesn't let current through, and that's going to be your 0 and 1. And that's how you sort of represent data, right? What these guys discovered, they were Albert Ferret and Peter Grunberg. What they discovered was this giant magnetoresistance. They figured out that if I've got two magnets, that are both oriented in the same direction, with an insulator in the middle, then current will pass through it because of this quantum mechanical thing called tunneling, where the electron will actually go through a barrier because they're equal magnetization, But if they're opposite magnetization, then it's going to get stopped. And they were like, okay, that could actually be our 0 and 1. And then what you could do is you could control whether it's a 0 and 1 based on the direction of the magnetic field that a particular piece of physical thingy had.
Yes.
Right? And so the way that the hard disk actually works is you've got this reader.
Yes.
Okay. So there's a reader that comes down and it's like reading the hard disk.
Like a record
And the hard
player.
disk is, yes, exactly. It's a record player that's like coming down and the hard disk is spinning. And the reader actually has these two things. Okay. The top one is rigid. It's going to stay fixed. The bottom one is going to flip based on the way the disk is moving. Okay. So if at the time of the disk, the magnetic field is this way, then the bottom one is going to flip this way, and it's going to let through current.
Yes.
But as soon as it moves and the other one is this way, it's going to flip this way, and then it's going to stop current. So now my little record player can read zeros and ones, and you can pack these little magnetic things super close and have a hard disk that is electromechanical because it's electrical, but it's also mechanical because it's spinning.
Yes.
Right? And then that is going to be my sort of memory. And now all of a sudden we went from like memory being stored in like things that were the size of refrigerators to like things that could be stored in the size of like a computer, a desktop computer. Right? So that was a big deal. 2007 they won the Nobel Prize for it.
Okay.
Well deserved. Right? And so that was sort of the first big win for Spintronics.
Got it.
Okay.
It was proof that using both
charge
and spin in
of the
combination
electron.
can have like production commercial application.
Yeah.
Yep.
Exactly. Right.
Okay. Yep.
So now it's like, okay, like what can we take this further?
Right.
Because if we could have RAM that was magnetic, right? Then all of a sudden, like, you know how like you're working on a Word document and then the power cuts off and you just lose everything.
Yeah.
Like I had that during finals week actually. Dude, junior year, this one time I was working on my paper. Right. And I had like worked, but like an idiot, I didn't save. So it didn't go to the hard disk.
Because we still had to manually save.
Yeah. Because we still had to manually.
There was no auto save.
Right. Yeah. So I didn't. And then the power cuts off for some fucking random reason. And then all of my stuff was gone.
I literally like
because the RAM didn't store it in the hard disk, but the RAM is a bunch of capacitors. So if you lose power, then the capacitors go, and then I lose everything, and then I log back in. The computer's like, "Do you want to go back to the previous save?" And it's like from like yesterday, you know. And so imagine if we had a magnetic RAM. Where the memory was stored in the polarization of these magnets.
Right.
Now, if I take out the power,
it can maintain.
Magnets are going to maintain their polarization.
Yes.
Right? So I could have this like way without like this non-volatile. It's called volatility in a memory. But I could have a non-volatile memory.
Yes.
Because it's stored in the physical orientation of the magnets.
Yes.
Right?
Yes.
Okay.
Yes.
So that's a great goal.
That's
and that's what we want.
That's
and then we can actually bridge this gap between memory and processing, right? Because now all of a sudden the same paradigm that we're using for memory, we can start using for processing, and it could be this like bridge between the two. And so now we don't have this von Neumann bottleneck.
Yep.
Okay.
Yes.
So this is great. We want this.
Yes.
We want this.
Yes.
Okay. There are problems. Okay?
As there always are.
As there always are. There are problems when it comes to what we want to do is we want to reliably switch the magnetization state.
Yes.
Right? We want to be able to say, okay, this particular unit has a magnetization state of 1. We want to reliably switch it to 0. Okay? How do we do that? Well, usually what we do is we use this thing called spin orbit torques, which use this thing called the spin Hall effect. Okay. And the way that you can imagine this is basically electron spins when you put it through a heavy metal. The heavy metal has a bunch of electron spins that are moving up, moving down, right? Uncorrelated. When you put a current through it, the spin up ones are going to go in one direction and the spin down ones are going to go in the other direction. The way you can think about this is kind of like the Magnus effect. Okay. If you've ever seen the Magnus effect, you've got a spinning. There's like these videos of like a spinning basketball that's like thrown down, and because it's spinning, the way that it interacts with the air around it makes it move in one direction or the other, right? Yeah. So if it's spinning this way, it's going to move in one direction. If it's spinning the other way, it's going to move in the other direction.
You know where I've seen this is in all those Dude Perfect videos where they try to throw a basketball off of like the Hoover Dam, right? And they spin it to in a particular
That's
way.
exactly right.
to
That's
go,
exactly
you
right.
know,
That's
to
the
move.
Magnus effect.
Yes.
Right? So the spin orbit torque is literally like the Magnus effect happening with electrons and an electric field, right? You're driving a current this way, and the spin in one direction is going to move it this way, and the spin down is going to move it the other way. So what you can do is you can have like this heavy metal layer where you're putting the current through.
Yes.
And a ferromagnetic layer, which is where the magnets are, and in a ferromagnet, all of the spins are in the same direction, right? That's what gives it its big magnetic field, like, right? All of the spins are in the same direction, so they all add up to give it a magnetic field. So now, if underneath I have this like heavy metal layer, and I have the spin going up is going to go towards the ferromagnetic layer, and it's going to apply a torque on the ferromagnetic layer, and it's going to change the ferromagnetic layer's magnetization. So all of the magnetic fields in the ferromagnet are going to switch.
Yes.
Okay?
Yes.
So that's usually how we want to manipulate the magnetic field of these little devices, right?
Makes sense.
It's like okay, you want a 1, I want to switch it to a 0. I'm going to poke it underneath with this current. The current is going to induce the spin orbital effect, and that thing is going to switch the ferromagnetic layer on top. And then now all of a sudden the thing that was a 1 is now a 0. Okay.
Yes.
The problem with this is there's a lot of dissipation, okay? There's a lot of stuff called Joule heating, which is just like the friction. Okay. There's a lot of friction that's going on.
Nothing to do with vapes.
Yeah.
Nothing to do.
Nothing to do with waves. Joule meaning Joule, like the joule of energy.
Yes.
Although I'm pretty sure the vape is named. It might be. That's something that we should research. Yeah. There's also a loss of angular momentum because like all of this, like just like Joule heating, the friction is going to lose a lot of the spin, right?
Yes.
So what these guys did. What these researchers from Korea, they actually used the dissipation of spin to their advantage. It's something that no one really had thought of before. Everyone's trying to minimize the dissipation of friction.
But they're like, what?
But they're using the friction to their advantage. They're actually leveraging the friction. Okay. They had this idea of using the intrinsic spin currents of the ferromagnet itself. Okay, because there's two types of currents, okay? There's the electric current, which is literally electrons moving. But you can also have a different type of current, which is a spin current, okay? So a normal current is just electrons moving in this way. There's more electrons moving this way than this way, so there's charge transferred. A spin current is where the electrons spinning this way are moving this way, and the electrons spinning this way are moving the other way, okay? So now you have the total electric current is 0 because the number of electrons moving left and the number of electrons moving right are exactly the same. So there's no charge transfer, but there's a transfer of angular momentum because the spin up is going this way and the spin down is going the other way, right? So you can now start affecting magnetization without actually affecting charge. Right? And so what they did was they said, okay, like what I can do is I can have a ferromagnetic layer in the middle, which has all of the spins aligned in a certain direction, and I'm gonna run a current through that. Okay, now the spin up is gonna go one way, the spin down is gonna go the other way. Okay, and I'm gonna surround it with an insulator on the top and bottom. Okay, but one of these insulators is gonna be different than the other. The one on the top is just gonna be a normal insulator. It doesn't like charge. It doesn't like spin. Okay. So all of the spin that goes up is going to just bounce right off. Okay. The one on the bottom is going to be something called an anti-ferromagnet. Okay. So a ferromagnet is when all of the spins are aligned. An anti-ferromagnet is when all of the spins are exactly alternating. Okay. So it doesn't have a big magnetization, but like it can act like a spin sink. You know what I'm saying?
I do.
It can act like an angular momentum sink. So now when I put it through the middle and I have all these spins going everywhere, the ones that go to the top that are of a particular spin are just going to bounce right off. But the ones that are going to the bottom are just going to sink into this anti-ferromagnet. And so the stuff that goes to the top, it's going to bounce right back, and it's going to start changing the spin of the ferromagnet in the middle. So now using spin dissipation, which is all of the spins are dissipating at the bottom, using this friction, we're actually taking the leftover stuff and we're flipping the spin.
Yes. Yes.
It's so interesting, dude.
That's so, and it was a way in which to find these sort of combinatorial dynamics in a way where it's like we're just like now engineering like what happens.
Yeah.
Such that we get an intended outcome.
Yeah.
And the intended outcome now is instead of the spin dissipation just being a loss.
Yeah.
You now make it a functional
Now the
component.
loss is actually the point.
Right.
It's crazy,
Right.
dude. Like the loss, the dissipation is actually the point of the whole study.
Right.
And from this, they've actually made a device that is up to 3 times more energy efficient because they're harnessing the loss as a feature, not a bug.
Right.
It's very nice.
This is such a good point about why framing and perception matters in terms of like, because the initial context is like, oh, this is just functionally a loss in the system, and there's nothing we can do about it.
And everyone's worried about minimizing it.
Right.
Everyone's worried about like, how do we get the joule heating down? How do we get the dissipation down? And these guys are like, no. Actually, the more the dissipation,
Right.
the better the fidelity in my switching from 0 to 1. It's pretty crazy.
So it's like it's using the dissipation as almost like this not a validation system, but it can create a consistency. Now, I think what's so interesting about this is kind of goes back to why it's important to be able to have so many people attacking the same problem from different directions.
Yeah.
Because the problems are so open-ended and like the blue ocean.
Yeah.
Like,
It's like there's no playbook.
Right.
For Spintronics, right? Because it's such a new concept. Right? Yeah.
Do you think that this is going to bring because of the...
I think this could be big.
So even if just from the... So let's take out commercial application for a second. Even just from now inspiring other research institutions to
it's a proof of concept that like, okay, this is a total different avenue that we've not even bothered exploring.
Right.
Now we can start exploring.
And there's some viability there.
I can definitely see some like research labs now like starting to take this more seriously.
So if you're a future PhD candidate, this is an area
this is really cool. And the other thing, I mean, the commercial applications are actually really cool because like the architecture that they used is super simple. It's a single ferromagnetic layer and a single anti-ferromagnetic layer, which is actually super easy to construct with like normal silicon fabs.
So,
right. So it's not like some exotic material that they had to dig out of the ground or something, right? Like this is just like nickel, silicon, oxide, like stuff that normal like chips are made out of. Like so it's not that exotic to like try to now replicate this and make this bigger and make this smaller and blah blah blah.
So to extrapolate from that, so the kind of what you're saying is, if I already am TSMC or I'm Foxconn and I'm assembling Apple chips or all these other chips, and I have this machinery infrastructure,
it's not too difficult.
I can potentially, there's some reuse of my existing infrastructure from a mass manufacturing scale perspective, where it's like we change order of operations, some of the ingredients.
It's like viable.
It's viable
in some sense.
It's
like, I mean, there's still a lot more that needs to go on in terms of connecting this to modern infrastructure and like current computing infrastructure and things like that. But the viability of this is not like something that's like really far ahead.
We don't have to rebuild the entire stack.
No, we don't.
Scratch in order to. That is actually a very important.
I think it's an important point.
Fascinating. That's not where I thought we were going to go with our K-pop demon hunters starting point. But using electron spin to an advantage, one man's trash is another man's treasure.
That's exactly what this is. Yep.
Which is so fascinating.